All right, students, I'm trying. This is my third time to try to record this. I've had really a hard time with my programs that I've been trying to use. I can't get them to upload, so we're going to try one more time. I'm totally going old school now. Um, Chapter 20 is where we're going. In your textbook, it's on page 915. I'm going to go quickly because we're so far behind. And we're going to just hit the highlights of chapter 20. It is a very easy chapter in my mind. And it's about balancing equations again, but this time it's nuclear equations. So we're going to talk about nuclear stability. You see in here, these are the things that we're going to cover. We're going to spend especially a lot of attention on nuclear reactions, what natural reactivity is, transmutations are, and these two, the difference between these two, and then modern day uses of these isotopes. That's what we're going to talk about in chapter 20. Okay, we're going to start with the most important ones, the reaction types, the two different types of reactions, nuclear reactions, and how they compare with chemical reactions and what we've talked about so far in chemistry. That's where we're going first. Okay, so in your textbook, this begins on page 916, and let's compare the two. First of all, you need to know what radioactivity is. We know that nature wants to be stable. That's just the bottom line. Water seeks its own level. You've heard that. Stability is where it's at. So that's where it. That's where we're going. You know that atoms contain protons and neutrons in their nucleus, and those are called nucleons. Together, protons and neutrons, if it's in the nucleus of an atom, it's called a nucleon. Okay, if it's in the nucleus of an atom, it's called a nucleon. And so balancing those nucleons, let me get a different, I got a different colored pencil. These are protons and neutrons that are inside the nucleus of an atom. Okay, if those are not stable, if the mix of protons and neutrons are not stable, then that's called radioactivity. And when we think of radioactivity, we automatically think that it's bad. But we use radioactivity for a lot of important good things today. So spontaneous emission of the particles from those unstable nuclei are what we call radioactivity today. And if we know today that if the atomic number is bigger than 83, then they have unstable nuclei, and we're going to talk about why that is. And then here's another new word to you probably, transmutation. This is what they did with the atomic bomb in 1947 or 45, I'm sorry, December of 45, when they bombed Japan and ended World War II finally. They bombarded the nucleus with neutrons or other things, and they caused an atom to fission or split and caused the bomb to explode. This is transmutation, when you purposefully bombard or throw things at a nucleus and cause it to be unstable. That's transmutation. Okay, so let's talk about nuclear reactions here. Let's talk about the difference, first of all, between regular chemical reactions that we've talked about up to this point and nuclear reactions that we're going to talk about in this chapter. And this is in your textbook on page 916. There's this table that's in the bottom that this is very blurry, I'm seeing on the screen here. But in your textbook, it's very clear. And some of the highlights are that in chemical reactions, those atoms get rearranged. For example, one of the reactions that we talked about was a single replacement. You did this in one of your labs. You had some zinc, and what happened there was the zinc took the place and kicked the hydrogen out and gave you hydrogen gas plus zinc chloride. This was a single replacement reaction. Well, here you just had this bond right here got broken, split apart, and then the zinc took its place, and so those atoms were rejoined. That's what happens in a chemical reaction. Atoms are rearranged by breaking of bonds, the bond between the two, and then rearranged. But in nuclear reactions, those bonds aren't broken. It's actually in the nucleus that these take place. So those elements, it's actually, hydrogen stayed hydrogen, chlorine stayed chlorine, zinc stayed zinc. Those elements stayed themselves. Okay, but in nuclear reactions, the actual elements change into new elements, different elements or isotopes. In chemical reactions, it's only the outermost electrons that are involved. But in nuclear reactions, all three particles, protons, electrons, and neutrons, and even other positrons can also be involved. Particles, alpha particles, can also be involved in the reactions, unlike with chemical reactions where you're only talking about the electrons. With chemical reactions, you have either absorption or release of energy or heat, but they're little amounts. Okay, you can have a color change, you can have a little bit of heat generated or given off, but with nuclear, there's large amounts of energy that are either released or absorbed, huge amounts. And then with chemical reaction, we can influence how quickly those reactions happen by messing with the energy, the temperature, the pressure, the concentration, or by adding a catalyst. Those do not affect nuclear. We can't affect the rates of the reaction by temperature, pressure, or catalyst. Now we can control, which we'll talk about later, but we can't usually affect by temperature, pressure, or catalyst. Here's the big one. Here's the big page right here. This slide is super, super important. I want you to know this page cold, and it's in your textbook on page 916. I want you to know these symbols. The symbol for a proton, there are two of them. I don't care which one you learn. You don't have to learn both, but you need to learn one of the two. A 11H or a 11P. Either one of these will work for the symbol of a proton, because we're about to learn how to balance these kind of equations. A neutron is symbolized with a 10N. The one on top, that's the mass number, just like when we were learning, for example, if you had an 18,8O, this is oxygen. Remember doing these? These are oxygen with 8 protons and 10 neutrons. To find how many protons, this is the atomic number down here, and this is the mass number down here. It tells how many protons plus neutrons added together. So to find the number of neutrons, remember you subtract it to get the number of neutrons. 18 minus 8 is 10. That's how you get that. You've got to know those. Okay? So a 10N is a neutron because it has no protons in there at all, so its atomic number is 0, and it's only got 1 neutron. These two are the symbol for electrons, a 0, negative 1e, or you can use a 0, negative 1b. That funny looking b is beta particle, which we're going to talk about here shortly. Then a new word, positron, a 0 plus 1e, or you can use a 0 plus 1 beta like that. And then the last one, the most common of all, is a 4,2 alpha. That's how I make my alphas. Or a 4,2 He. These two mean the same thing. This is an alpha particle. They're the most common. They're the least penetrating. Okay? A few sheets of paper will stop an alpha particle. All right? I'm going to show you on Blackboard also. Let me just see if I can quickly draw for you. If you're on Blackboard and you go to that math launcher, You remember the math launcher screen? There's some tabs that are up here at the top of that math launcher screen. I'm probably going to do another video. One of them has little boxes that look, well, I'm terrible at drawing, that look like this. If you'll click on that tab, it will open a screen for you to be able to enter in these superscripts and subscripts. I'm going to do a little video to show you how to do that here shortly, because you're going to be required to do that. Okay? Please understand the difference between a regular 0, -1e and a 0, -1 beta. I want you to understand the difference between the two. If it's a regular electron, a 0, -1e, that means it was an electron that came from an atomic orbital, from the outside around the nucleus where electrons live. Okay? If it's a 0, -1 beta, this is an electron that came out of the nucleus. How in the world can that happen? How can you have an electron that lives in the nucleus? Well, this is how. The fact is that when we talked about protons, electrons, and neutrons, and I talked to you about that a proton lives in the nucleus and it has a mass of 1 AMU, and its job of it was to identify what the element was, and that the neutron, its job was to hold or bind those protons in the nucleus, and it had a mass of slightly more than a proton. The reason that its mass is slightly more than a proton is that a neutron is actually made of a proton and an electron, and they are actually glued together by a particle called a gluon. Now you won't have to know this. This is just for you that are curious. It's a V, this symbol right here with a little bar over the top. This is physics now. This has so little mass that it's almost immeasurable, but it's inside with this proton and this electron, and it's holding these two together. Now, if something happens in the nucleus of an atom, this is a neutron right here. Okay, slightly bigger than a proton. Remember what its job is. Its job is to hold those protons in place in that nucleus. If something is to happen, though, that shakes up the nucleus bad enough that the neutron splits open and gets damaged, the proton can stay in the nucleus. It's going to be allowed to stay in the nucleus because protons live in the nucleus. That's where they reside. However, this electron here cannot live in there. The other neutrons are going to say, oh no, buddy, you cannot stay here. Get out. And if it's kicked out of the nucleus, it is a beta particle. It's a beta particle. Now the gluon also goes, but again, for chemistry purposes, we will not talk about that. And if I was teaching you physics, then we would balance that gluon as well. Okay? So that's what this is talking about. So if you have an electron that leaves the nucleus through beta decay, it means that a neutron was damaged and the electron had to leave. So the positron is also the same way. It has got the exact same mass as an electron, but instead of having a -1 charge, it has a +1 charge. And then we're going to talk about an alpha particle. Alpha particles are totally cool. You're going to represent those again with a 4,2He. This is an alpha particle. That's how I'm going to always show it. Some people like that draw that alpha symbol better than I do. They like to show it like that, but I'm terrible at drawing, so I'm always going to show it with a 4,2He so that people can tell it better. Okay, so we're going to practice now. We're going to draw some, we're going to balance some equations. We're going to do, you would do a whole lot more of this in physics, but we're going to do some of these equations. Balance some nuclear, what they're called nuclear equations. This would take place if that nucleus of an atom was unstable. We're going to talk more about the stability of a nucleus, because remember, that's what it's all about. Is that nucleus stable? Did something happen to make it unstable, so now it has to rewrite itself and make itself stable. What happened to make it that way? So, just like when you balance in regular chemical equations, you must remember that here's your yield sign. Everything on the reactant side, on the left side of that yield sign, has to equal whatever's on the right. Okay? Everything has to balance. It must balance itself out. So the total of the tops, those mass numbers on top, must equal on both sides, and the total of the atomic numbers that are on the bottom must balance out on both sides. And then you're going to use the periodic table quite a lot. And so far we've used mostly the top of the periodic table. But now we're going to use the bottom half quite a lot of the periodic table, because that's where most of the radioactive elements are, is at the bottom of the periodic table. So we can identify those if we have an unknown by its atomic number. If you know what the atomic number is, you can look in your textbook and you can look at your periodic table, and you know that the atomic number, I don't know what I did, the atomic number here is the number of protons, and so you can look at the atomic number, number 99 in this case, is Einsteinium, and so that if we that was our total, then we'd be able to say, oh, there's Einsteinium. Okay? All right, we're going to practice those in just a minute. Let's try one. This is the example problem that's on page 917. We're going to see, identify the missing species. So we're going to say, what is our X? What is this? So we're going to find out. Remember, keep in mind that your bottoms have to balance. So I'm going to write this a little larger because this is blurry and I don't know how well you can see it. So we have on the top, we have 212, 84, PO, and then we have, that's polonium, and it's decaying, so it's unstable. The nucleus is not stable. Something happened, it's not stable. So it's going to 208, 82, lead plus what? So we know we have to have our bottom numbers must add to be the same. So if this is 84 on the left, then 82 plus what would have to go in this box to give us 84. 82 plus 2 is 84. Now look at the top. On the top we have 82 here. We have 208 here. So 212 is the total on the left. So 212 must be our total on the right. So we need something in this box that when we add it to 208, we get this total over here of 212. So this is going to be a 4. What particle do you know that's got a 4 and a 2 of these particles that we've just been talking about? What has a 4 and a 2? An alpha particle, a 42He, and you can choose to write it as a 42He, or you can choose to write it as a 42 alpha like that. I do not care which you choose. I do not care. All right? Let's do this next one down here. This next one says you have a 90, you have a 38 strontium, SR, and I'm going to put this one first even though your textbook has the X first. It has a 0, -1 beta, so something has happened to shake up this nucleus. It's kicked out a beta particle. Now, look at our total on the left. It's 38, which means that this plus this on the right, we're going to fill in these 3 boxes over here. The bottom must add to be, both of these 2 bottoms must add to be 38. So -1 plus what equals 38? -1 plus 39 equals 38. So this is going to be number 39. That's what's going to go in that box. And then the same is true of the top. The top is on the left is 90. So on this product side over here, 0 plus what gives us 90. Well, that's 90. Okay, so which one of these two numbers do we use, 90 or 39, to identify the element? We always use the bottom number. This is your atomic number. It's what identifies the element. So this number 39, we're going to look it up on the periodic table. And I see from my periodic table that number 39 is yttrium, which is capital Y. So this is my answer, 9039 yttrium. That is the answer. And then lastly, I know what my products are, but what was my original? Again, on the right side I have an 18, 8 oxygen, plus a 0, positive 1 positron. So on the right over here, I know my top number has to be a 0 plus 18 is 18. And on the bottom, I have a 1 plus 8 is 9. And on my periodic table, I'm going to look up atomic number 9 because it's what identifies the element, the atomic number. Never look up that top number. It's the bottom number that identifies the atomic number. And this is fluorine. So there's my box right there. And that is worked out for you on page 917. That's your answer. So X is equal to, and then there's more for you to practice on page 917. Plus I'm going to give you some to work on as well for your homework. Okay? And then this shows you how to work it out, and that's worked out for you on that practice problem. In section 20.2, this just gives you some patterns of stability that are in your book that are just kind of neat things that you're not going to have to like know. I expect you to know, really know that first section, section 20.1. Know those particles, know how to balance those equations. I really expect you to know that very well. So on nuclear stability, please understand that it truly is all about the nucleus becoming stable. It really is. So remember that the nucleus does take up just a very small part of that atom, but it has almost all of its mass. And it talks about here, assume that a nucleus has a radius of about 5 times 10 to the negative 3 picometers. Now that's tiny. And remember that density is mass over volume. So it says to calculate the volume of this, and so we're not going to really talk about that. But here's what I said on my other PowerPoint that I made for you that I couldn't get to load. If you took the Dallas Cowboys Stadium, the new one, and you were to put the nucleus on the 50-yard line, and the nucleus was as large as maybe a baseball, that would be about right for this size of a nucleus when you compare it to the entire size of the Dallas Stadium. And yet, it would weigh as much. Think of a baseball now. Think about that size. That would be the size of the nucleus. But it would weigh as much as the entire stadium in that size of that baseball. So think about that with me. And yet, all of its mass in that tiny baseball, that's how dense it is. That's how tightly packed it would have to be. Okay? So the average atomic nucleus is this big, 9 trillion times as dense as the most dense element known to man. It is so dense. We can't even imagine how thick it is inside there. It is just crazy. And we're not going to talk about this too much, but I do want you to know this. The most stable isotopes, they have very low atomic numbers. So the small atoms are very stable, and they have a 1-to-1 ratio. For every 1 proton, there is 1 neutron. okay, 1 to 1. But as their atomic number, as you get more and more protons, well, think about what's going on here. Those like charges, they repel each other. They don't like each other. And so the more and more protons that you get trying to pack into that tiny little spot, really packed tight, they don't want to be together. They don't want to be close to each other. Like charges repel. So you've got that repulsive force trying to get away from each other. The stability just goes off the charts, just becomes more and more unstable. So the job of the neutrons becomes very difficult indeed. So you have to have more and more neutrons in there to hold those protons in and keep the stability in place. That's the job. Now there are some patterns. Now again, this is just kind of interesting, but the more stable atoms are those that have 2, 8, 20, 50, 82, or 126 protons or neutrons. They, for whatever reason, are very stable, and so they're called magic. Magic numbers because they're extra stable, okay? And so if they're even, they have a higher chance of becoming extra stable, and then it gives you this pattern of stability. Isotopes that are odd happen to be radioactive. And so this is just interesting information. And again, in your book on page 919, it gives you this graph, and it's in pretty color here. I'm going to put this on Blackboard for you, this PowerPoint as well, so you can see it. But it shows you this belt of stability, and it's just kind of showing you that most of the time the radioactive elements are going to lie outside this belt. So if it's not along this belt of stability, if you have a proton to neutron ratio that's doesn't lie on this belt, it's going to be radioactive. Now we're not going to have to know that too much, but what I do want you to know is how it writes itself. So here's an unstable nucleus right here. The proton to neutron ratio isn't good, so how does it write itself? See, this is not a 1-to-1. That's not a 1-to-1 ratio. This, oh, I don't know if you can see that. That says 14,6 carbon. This is a light element. That's not 2-to-1. You know, it's not a 1 carbon for every, that's not 1 proton for every 1 neutron. It's got a couple extra neutrons in there. This has 8 neutrons and 6 protons. So the mix is not good. So how is it going to write itself? It's going to get rid of a neutron, and it does that by beta decaying. And it beta decays, kicks out, splits a neutron open, and the way that it does that, remember I was showing you what a neutron is actually a proton and an electron. So it splits that neutron open, it lets the proton stay, kicks that electron out. And now look what you got. You got a 14,7 nitrogen, and it kicks that extra electron as a beta particle out. Now it's extra stable. And those other examples here as well on how that happens if the mix is not good by beta decay. Okay, same thing is true if it's not stable because it doesn't have enough neutrons, then it might positron decay and get rid of a positron, get rid of a proton in the nucleus. And that's what's happening here. Okay, but I'm going to let you work on those nuclear equations. I'm going to give you plenty of those to see, and it might also capture an electron. And if it captures an electron, then you don't use the beta particle, you use this instead. So that's what it's talking about right here. Okay, and if it captures one, then it shows you exactly what's going on here. It's going to create a new nucleus, but again, you're just going to balance them out. That's all you're going to talk about, all right? And I'm going to talk about binding energy in a different video.